let's give it another try. I mean, where did we leave last time? So basically, I came across some things that I know that are true about the density matrix. The one is it's not an alternative representation of the state vector. It's in the sense that they are mutually exclusive. It just shows us some more information that we can't see in the state vector. The diagonal items, the diagonal elements seem to indicate the probability of those particular states, 0, 0, 0, or 0, 1, 1, etc. I don't know yet. I don't know yet what the off-diagonal elements mean. What else did we come across? Is that really all? Or is that all I remember? Because I wanted to play. What happens? I wanted to mess with like. I remember there's like. Let's play with some stuff. Like let's just make some random gates and see if we can get some messy. Some messy things in here. I don't know what I'm doing. So that's cool. Okay, let's see what happens, because you see now I have this. Okay, so now we have these things where some of them have like really low probability. So how does the density matrix look like? I think you can barely distinguish these, but if you can see, some items are a bit darker. A bit darker. 0.233 versus 0.017. Okay, so this indeed it's something to do with, but like why? What is this, for example? What the hell does this mean? Oh, I can click that. That's nice. And if I add a Z, what? Okay, but it's kind of changed the sign on. It's like none of the diagonals, and obviously we'll take a look at the state vector. So it's done this for for all the states that start with 1, right? Because these are the ones that start with 0, and so this seems to be in this case exactly what's happening here. So the basically these kind of correspond to the ones that start with 1, and yeah, and this as well, but on this side, right? Okay, sure. And if I move it here, then it kind of breaks down because it's a qubit in the middle. So okay, and then some of them have like, it's different, right? Minus 0.017, minus 0.233. So there's definitely, yeah, but it's just like that's all good. Ooh, wait a second. So basically, and I think, and they seem to be complementary in the sense that the empty squares in here are full in here now, and this is because we've applied the S gate, which is a rotation. Yeah, but isn't, of course. So if I apply another S, then it brings those up in here. That's a pretty cool visualization, though, I have to admit. Which is the same effect as applying twice, as applying one time the Z, which we're doing now. Okay, what about the T? That's interesting. Because the S removes the squares from here? Huh. That's interesting. So you see that's something you definitely don't see in the state vector. In the state vector you just see that the S, versus if I apply a T, you're gonna get the purplish thing, because okay, so and this is exactly what I'm so because the real and and the complex components are not like they both have information, none of them is zero, right? And that's why you get this kind of purplish color. And the way this looks like in the density matrix is these probabilities are still all there, but they are less, and then there's a bunch of complex ones here. But still, why is this blue and why is this pink or red? Because this is negative and this is positive. Okay, but what does this mean? I mean, in the state vector, you see in the state vector there's no negative sign at all. It's all positive. So that's even more confusing. Boah, mind blowing. So they have to have this has to have some meaning. It's like, and what happens if I put a Z and now I swap? Bim. Yeah, okay, so it has the same effect as then having just the Z on the qubit 1. Okay, good. This doesn't do anything. Control Y. That's some weird stuff, man. So again, complementary, right? So what's the state vector? So it's changed it's added complex, it's added the complex and negative, right? Here's complex and positive. Complex negative, complex positive. And so you can see so let's take a look at, so what if we try to read the matrix row by row? So here you've got, so the difference, you could have this into like a weird thing that you pack together where each cell has the real and the complex. So but that's clear, the one is the real component, the other one is the imaginary, the complex component. 0 0, right? So 0 in here it says both real and imaginary are positive. Let's check that. This guy. No. Sorry. Positive? 0. Correct. So let's try to read this column by column. Maybe it's make it easier. 0, negative, 0, negative. Correct. Now it's going to be positive 0 and then 0 positive. Positive 0, 0 positive. Okay, now should be positive 0, and then positive, and then no, then 0 negative. Set positive 0. Yeah, it seems to match, right? So this is literally it literally, so that's how they color code. It literally means whether it's positive or not, positive, negative, or 0, and then so you've got that. But then what? So what is the second column, for example? Because mm, this is what I don't understand. I don't understand. I don't understand. A question that I have is, if I do like y, y, and y, why is that? So if this is, and now this is even more counterintuitive, because if this is it has a negative complex component, why the heck it's in here? Wow. So this is even worse than I thought. So all what I just said now, it makes no sense, or at least gets invalidated because of this. Huh? Maybe this is not the complex part. Uh, the reason I thought it was the complex part is because I thought RE stands for real, and I thought that is IM for imaginary, because I mean, complex numbers are also called imaginary numbers. And it kind of makes sense, because when I was now reading through that, it just made sense. But but we just saw that with the Y's, it doesn't make sense. Hmm. This is indeed frustrating. This is indeed frustrating. Mm. So what the of matrix density matrix for dummies? I'm googling right now. Yeah, so we learned about pure states and mixed states as well. Mm, check that. Reddit physics. What's the significance of diagonal elements of density matrix? The general impression I get is that they somehow represent the amount of coherence since performing a measurement, but forgetting the results kills all non-diagonal entries, and things like phase errors make them smaller. Then again, the density matrix is basis dependent, so maybe it doesn't make sense to refer to the off-diagonal elements. Mathematically decrease in value of off. Uh-huh. Mathematically, a decrease in value of off-diagonal terms represents a loss of coherence regardless of initial values. Mm, is it that maybe, give me a second, maybe, does this mean that maybe with time this decays? So this is an indicator of, what if I keep adding stuff in here? It seems to be the same. I had a stupid idea that I thought maybe by maybe I just copy paste that many times. uh, no, it stays the same. I had this stupid idea. Maybe those values will decrease with time, so this will be an indication that your circuit is already too long or something. I don't know. Hmm. Because those numbers make absolutely no sense to me right now. Whatever is off diagonal, they seem to have a relationship with the whether the amplitude is positive or negative, because then they switch to the pinkish. But it's like, why would that element, which is the intersection between 000 and 011, why, what would this mean? Those are just like, that's what's kind of confusing. So just good job. Good job with this. Let's get rid of this. Let's get rid of this. So they could add a little explanation here, maybe. The off-diagonal elements R, I, J of the cinematic proof provide information. Provide information about the interference between the amplitudes of states I and J. Really? Mm, no, a lot of mass. So it's information about the interference. But what is the effect that this has? What does this tell us while building the algorithm? That's, or why, while, what's practical about it for someone who's building an actual circuit? Mm, it's a writer. I don't know what I'm doing already. Statistical mixtures. Is there anything here like off diagonal? This is just a probability. Okay, look. So the diagonal matrix elements have a simple physical interpretation. It's just a probability to find the system in this state. Similarly, the off-diagonal elements are called coherences. Note that it is possible to choose a basis in which this is diagonal, since this is Hermitian. In such a basis, the coherences are all zero. Okay, so it seems to indicate this is really something to do with the interference or the noise, or no, maybe it's not the right word. But how is that supposed to help me? How is it supposed to help me while building a circuit? I don't know. Mm, maybe you want to have, it's kind of weird, because then it would make sense that you would see that with time sort of decay, and then it would kind of be an indicator to tell you your circuit is probably going to lose the quantumness. Okay, but at least we've learned, so now we know the diagonal items are definitely it's a probability of finding that state. The off diagonal elements are, is like physical interference between those two different states, whatever that really means. So it's sort of yeah. Hmm. But what does this tell us? That's exactly what I'm missing. That's exactly what I'm missing. What does this interference tell us? Um, why is interference between quantum states important? Maybe that's a better question to ask. The role of interference and entanglement. Oh. Let's see. Interference. Boah. In Grover's search algorithm. Interesting. So this page 21. Why doesn't this never get the right page? That's a long that's a long book, or whatever that is. Okay, so quantum mechanics harbors some of the most bizarre and counterintuitive phenomena known in physics. One of the first phenomena to be observed was interference. This phenomenon was already widely known in the context of waves, but it came as a big surprise that matter sometimes also behaves as a wave, in addition to its particle behavior, and therefore also exhibits interference effects. Because the matter wave can spread in space, it can destructively and constructively interfere at certain positions. Interference in the quantum mechanical formalism is relatively easy to understand, yet its applications are stunning. We know the effect of a Hadamard transformation on the basis states. Correct. These guys here. Yeah. On 0 is this, and on 1 is this. Now let's suppose you have a qubit in state that, and we apply a Hadamard transformation. We thus get the state this 0. Yeah. We see that the last step, the amplitudes of 1 have interfered destructively. Yeah, this is they cancel. Yeah. Moreover, as the amplitudes were equal in magnitude but opposite in sign, the state does not have a component along 1 anymore. On the other hand, the amplitudes of 0 state have interfered constructively. I think I'm starting to maybe have a bit of a, it just clicked for a second because I saw the name Grover in the, and could it be that this is gonna could it be that this is telling us what really kind of cancels out and doesn't cancel out? Because one of the things so if you check out the video on Grover's algorithm, there was one thing I was talking about, um, positive certainty, negative uncertainty. I'll see if I can link it into the description below, because I made the point at an intuition level saying, um, that in Grover's algorithm there's a point where um, we basically flip like a big amplitude, and then we're trying to go with the Hadamard, applying Hadamards again. We can't go back to the state. For some, I can't even explain it. But I know what I mean. So let me, maybe I should just, uh, maybe I should just find the video. So what my point is, when let me see if I can find the video. So let me, I'll just mute myself. I sound awful. So here, and so what was happening here is, let me go. There's a point where exactly we're here, because I'm gonna try to reconstruct that circuit maybe. So we're here now. We flipped this to a negative, and so what I'm saying is, when we do that, and then we bring it back to 0, 0, 0, exactly. So now it's flipped, right? And then exactly. And now, and here's the point. And for some reason, it's like, still, I kind of like said, yeah, and then you apply Hadamard's again, and then it will just flag the state that we had originally flagged, which was, I think, exactly 0001, right? And I was like, yeah, it just kind of remembers that, right? And maybe this is what. Let's see if I can rebuild this. So let me see if I can rebuild this. So I had this, and I had this, and then I had Hadamard, Toffoli, Hadamard. Oh, fancy stuff. But look at this. Wait a second. Look at this. I think I am on a good track. So this is the only one that is flagged, and then all this here is minus. So this basically, what this is saying is, this saying that they will cancel each other? I don't know. The Audemars, so this, then we've got the X, the Audemars and the X. So we've got this. It's cool because it seems like it's literally like the negativity is concentrated on one point. It's pretty cool. Now we're here. That would be cool. Maybe I just should actually do that in a separate video, like Grover's algorithm from a density matrix perspective. Now I apply X again. Fancy stuff. And now, where am I in the state vector game? So now I'm here. Density matrix. Yeah, those are kind of stronger than those. And this is super strong. Okay. Everything else is like weak, and this is really bold. And now we apply this thing again, and this, and this. Okay. ID. But that doesn't tell me. I expected something else. Because I expected that maybe this would somehow tell me. Wait, I still have to. Sorry, I still have to go back. I still have to go XXX. So this and this are weak. Um, but then you apply Hadamard's. That's all focused in here. That's exactly the element has been found, which is this one. But I thought that would give us, maybe it does. Maybe I should explore that more. Maybe I think that's gonna be. I'm gonna make the second video focused on this, because I think based on what based on what I read here, here. Maybe I should read farther. I think what this is telling me is that somehow the matrix tells me how are they going to interfere. So my point is, I have the suspicion that you might have. Is it possible that you might have two different states? No, the same state might have two separate. No, it's not possible that the same state has two separate. No, two separate representations. But basically this is supposed to be telling us, okay, for example, this what between this and this, they have like a negative something. Yeah. I think I'm on the right track. Don't worry. I think I'm on the right track.